Okay. Do lots of things periodically here. Like start class on time. All right. You guys like chemistry jokes? Well.
Oh, I'm so close to
Two sodium atoms are walking down the street. One goes, "Oh man, I think I just lost an electron." And one's like, "Are you sure?" One's like, "Yeah, I'm positive."
I never
yes.
want to hear that again. No.
Never want to hear it again. Okay.
No, that was good.
All right, Jed, I think you asked this question what the different types of radiation are. Right? These different units. So here you go. So the base unit is a becquerel there. It's the count per second from the it's just how many things break apart. So just how many photons, how many alpha helices, how many beta, and a Curie. So a Curie, that's a unit that's from Marie Curie. It's that many 73 billion becquerel. No, 73 trillion. I'm sorry, 73 trillion becquerel is a Curie, and then let's see here. And they're connected that way. So I usually think in rem. That's my unit. Right? So we have a sievert. Okay, the sievert is also 100 rem. Okay, so anyways, go back here. So a rad. We don't have gray to the Curies, but so. A rem is a rad, but multiplied by a factor that's biologically active. Like you've heard of the UV index before, haven't you? So I look at that. They take the UV wavelengths and they multiply it by the biologically effective, what damage it has on the body. So for a rem, you take for neutrons, it depends on what the energy of the neutron is, and for alpha, it's 20 times that. So, but with alpha though, it's different because if it's outside your body, it doesn't do that much damage. Inside your body, it does a ton of damage. But you're allowed to get people, the regular population in the United States are allowed to get 5 rem. You're allowed to get 5 rem. The most I ever had at one time was 400 millirem. It was with a CT scan. A full body CT scan is 1 rem. But this is what happens if you with your radiation dose. So nothing really happens. You're allowed to have, like I said, you're allowed to have 5 rem. That's just a law. That has nothing to do with anything. That's just what the Nuclear Regulatory Commission says. You can, if you get a certificate, you can go up to 10. So, which doesn't mean that much because you don't really feel anything till you're about 20. At about 20 rem, that's when you're white. That's when things start happening to your body. It's after 20 rem of radiation dose, and that. So the plant workers in Fukushima, they got about 25 rem. So they did you guys ever read the news on that?
Like just normally every day.
No, after the nuclear accident. Because yeah, the earthquake and the tsunami came, and then they were calling themselves a samurai. Like we'll risk the radiation damage. They're only about 25. I mean, which they can actually you will have a decreased white blood cell count, maybe cancer, but it's still pretty low. You can lose your hair at about 60. It depends on the person. So 60 to 100, that's when you start to lose your hair usually before radiation sickness. So radiation sickness, it's just you really it's just cell damage. So radiation doesn't necessarily give you superpowers like you see in the like the comic books or whatever. It's really it just yeah. Huh. Maybe if you consider cancer and radiation sickness superpowers. I mean, it's better than my superpower. I tend to hit every single red light, at least in downtown Kahului. It's my superpower. I'm a mildly inconvenient man, as I call myself. But it just causes cell damage. So I mean, like when you get a sunburn is a radiation burn. Okay, so it's well, at least I've only had a first degree sunburn. For burns, redness is first degree, blistering is second degree, charred blackened flesh is third degree. So that's I've only had a first degree radiation burn, sunburn. It's the most painful. I think second degree is more painful than first. So the worst one's third. Yeah, there's no going back at third. I've only had a few second degree thermal burns. One time I was doing glass blowing, scientific glass blowing, and it was this finger here. I hit I hit the molten glass on that finger, and I remember hearing like, oh no.
Ooh.
And then I didn't feel it right away, but later on it hurt really badly. I couldn't feel this area of my finger for about like 4 or 5 months. So the sensation did come back. But I mean, your nerves and your lower extremities can grow back. You look like you had to say something, Jet.
Christmas craft fair and with my new cousin, and we were using hot glue, and we were using she just poured some hot glue in my arm.
You put what?
She poured hot glue in my arm.
Ooh.
I was just like using it, and she was like, while she was doing it, like I didn't feel it while she was doing it, and I felt like something like charring my arm. Like, oh.
Did it blister up or?
Yeah, it didn't really touch it off.
Yep, that's
And
second.
only after I wiped it off, it started hurting.
Yeah, second degree burn. Yeah, I mean the same thing with radiation. Just like a thermal burn, thermal burns cause damage. Radiation causes damage. And satellites, like up in space, there's a lot of radiation from the sun and whatnot. They can corrode. I mean, not necessarily corrode as in like rusting here on Earth, but the metals can become fatigued just from the radiation being bombarded by it. So, but humans are fairly resistant to radiation. People think cockroaches are like amazing, that they're not. Fruit flies, I think, are the better ones. So a lot of, but generally speaking, the more complicated the organism, the more susceptible it is to radiation. So humans are more susceptible than insects. But cockroaches aren't like the kings. They say like, oh, there's gonna be cockroaches left after the apocalypse. Like, no, not really. So probably more fruit flies. But radiation sickness, if there is, I think I gave a brief lecture on this after we had the nuclear bomb scare. At least now it looks like the Korean War is going to end soon. So, and denuclearization of the peninsula. Have you guys been seeing that in the news?
Mm.
So actually,
Yeah, exactly.
the memes.
North Korea and South Korea leaders taking
Oh, yeah.
their full.
You showing like he saw the Korean dance and like, ooh, I like that.
Yeah. Yeah, the parts of your body that are susceptible to radiation, the most parts are your eyes, your hair follicles, and your stomach lining. So those are the ones that go first, at least in your skin. Yeah. Do you guys want to learn about this, or is this going to disgust you?
Pretty interesting.
Hanging up fall out.
Yeah, exactly.
Yeah. Yeah, I mean, so GI tract gets you, the skin lesions. I mean, it's much like a thermal burn. I mean, well, also with, like, I think I talked about this before, that dentists, anyone who works around x-rays and gets I mean, that's not shielded constantly bombarded with x-rays, their skin gets messed up. So some of the old nuclear scientists like Glenn Seaborg and some of the dentists that would go and like put their hands in patients' mouths, they would have like manky-looking fingers and hands. It's from all the X-rays and the radiation. Question?
We were talking about that too, about how this lady had cancer on one side of her face because she rode on the same seat of the bus to go to work every single day, and someone would hit that side of her face.
It was skin cancer?
That's skin cancer.
Huh. Well, because I was told that most skin cancers happen at an early age. Was this when she was younger or when she was older?
She was like 40.
Huh.
Some pretty similar.
Could be. I don't know. But, well, how cancer works, some of it we don't entirely understand. Cancer works by, first a cancer cell has to be created. Okay, so 2 steps. Cancer cells created, is created by a mutation. So, and it's a very specific mutation to create a cancer cell. So, I mean, usually it has to do it by damaging the cell's DNA. And chemicals are far worse than radiation when it comes to carcinogenic effects. So radiation is kind of a mild carcinogen, but other chemical means, things like hexavalent chromium, extremely bad for making cancer. But so cancer cell, so the DNA of the cell is damaged, and then it's repaired incorrectly, and then a cancer cell is created, and then somehow the cancer cell is activated. That's the other thing. And that's some of the steps we don't understand. So cancer cell is created, then it's activated, and then it can grow to form a tumor. So tumor is a growth. Tumor can be benign, which means it's either not growing or shrinking, or growing very slowly. That's considered a benign tumor. Those are not as dangerous. And there's a malignant tumor. That's when the tumor is spreading. The damage from cancer comes from either just the mechanical pressure of things. Like, let's say you have a tumor, a malignant tumor in your liver, and that pushes mechanically on the rest of your liver, and that can cause damage to the other parts of the body. Then the other thing it can do is that the cancer cells draw nutrients toward them, and it can kind of starve out the other areas. So that's another issue that cancer cells can do. And that's one of the things that cancer drugs try to, they target different things. One of them is to prevent the vascularization, the blood vessels from forming. So it'll slow down the rapidly dividing cells like a malignant tumor. And then your body's immune system can get rid of cancer. So it's not like, oh, if you have cancer, you're dead. But your body can fight it. And the idea of some of the chemotherapy is to slow down the growth, and your body can also, your immune system can clear out the cancer. So, but there's various different types of cancer drugs, but one of them is prevents the new blood vessels from forming, which is bad for people that are taking chemotherapy, because like if you bruise yourself, it takes forever to heal. And it can also, like your other rapidly dividing cells, like in your hair follicles and your stomach lining, that's why some cancer patients like have nausea, throw up, and the hair falls out. I mean, is this interesting to you guys, or I mean, this is kind of, because some people look.
Yeah.
Okay.
It's
All right.
important to know about. It's interesting.
Yeah. There's other types of cancer drugs. There's a class called the alkylating agents. So what they do is they're essentially mutagens. They cause reactions across the DNA. They'll combine the DNA into blobs. And for the fast-acting malignant tumors, it tends to kill those cells. Of course, it kills healthy cells too. The alkylating agents can also cause cancer. So not necessarily the ones that you're given for drugs for cancer drugs tend to be relatively mild. So an example of a very strong alkylating agent is mustard gas, the chemical weapon. It's a blistering agent. So it blisters you up, and then most people that get exposed to mustard gas also get cancer. So it's kind of an inconvenient sort of weapon, but then the side effects are pretty severe for mustard gas as well, because it pretty much says you're going to get cancer. But all right, so then radiation exposure. Other things that are endanger your thyroid. But that's only if you're close to a nuclear reaction, because iodine 131 can be released, and that goes right to your thyroid. Americans aren't too much at risk because we enrich our food with iodine. So as long as you're eating processed food or you put salt in things from I buy salt for like $1 for a pound at whatever Foodland, kind of thing. That has iodine in it. As long as or if you eat fish, at least fish from the ocean, that has iodine in it. So Americans tend to be pretty good at that because, like I said, we enrich our food with iodine. A lot of iodine's found in a lot of places too. Like it's in a lot of milk products because they use iodine compounds to clean the udders on the cow. So if you know anyone who's had to have an iodine-free diet before, you basically can have fruit and meat. Basically, you can't have any grains or nothing dairy. Sometimes not even meat, but meat unseasoned and unprocessed. So sometimes people have to go on iodine-free diets because of a thyroid issue. But you say something? You're just smiling. All right, and so where do we get our radiation exposure? So this is on REM. You're allowed to have 5 REM per year. Yeah. But so anyways, so where we left off though was with nuclear reaction. So we did talk about nuclear equations a little bit. That the top number, so here like the electron capture here. So the top numbers are the same, bottom numbers are the same. So the top numbers for top one there for beta decay. Or I'm sorry, that's positron emission. Sorry, positron emission. 1 equals 1 plus 0, and the bottom 1 equals 0 plus 1. So the top numbers equal, bottom numbers equal. So nuclear equations are very easy to balance. And we talked a little about this before, that here we have the number of protons, number of neutrons, number of protons on the x-axis, number of neutrons on the y-axis. And the idea is with the 4 fundamental forces, you have the electrostatic force, which if you have a bunch of positive charges in the center or something that you want to repel, but you have a nuclear force, nuclear strong force, which is stronger than the electrostatic force, so a nucleus is held together. But when you start putting more and more positive charges in there, the number of neutrons has to increase because the number of the neutrons also, they act like the glue. They add more of the strong force but have no charge, so the nucleus becomes bigger and need more neutrons. So then here is the curve of nuclear binding energy. So if you look at a free proton or a free neutron, it's actually more massive, generally speaking, than the proton or neutron inside of an atom's nucleus. So because when a bunch of protons, a bunch of neutrons come together, they lose some of their mass and form bind energy. And the mass loss, it equals mc squared. The energy is then the amount of mass they lose turns directly into energy. And so that's why things form. And most of the elements are formed in stars. So the Big Bang, after the Big Bang, the elements, hydrogen, of course, helium and lithium, and depending on the source, maybe a little bit of beryllium, depending on whom you ask, was formed from the Big Bang. So then the rest of the elements are essentially formed in stars. Some recent data suggests that some elements are formed via collision of neutron stars. So that's only been published this year. So, but the inside then the star's nuclear, inside this core of the star, of course the most, well, one of the typical reactions is 4 protons to form helium.
So this is even further down. So this is heavy hydrogen. This is deuterium. So hydrogen is the only element that we name the isotopes. The names of the isotopes for hydrogen is protium, deuterium, and tritium. No one calls it protium, by the way. But most people just call it hydrogen. So if you hear hydrogen, it usually means a proton. It means protium. This is deuterium. That's heavy hydrogen. But when helium is formed, you can see all the way up there. It's very, very exothermic. So making helium in a star is very, very exothermic. Also, the sun, our sun is a, we think, of course, this is astronomy, so everything changes every day. We think the sun is a third generation star, meaning the Big Bang happened, a star formed, that blew up, then formed other stars. One of those stars blew up, and then formed the sun. So we think that we're a third generation star, and the sun is also known as a carbon-12 star. So what happens in the sun is actually carbon-12, so it turns into oxygen, so 18, is it 18? Wait, turn 12 plus oxygen 16. Okay, so carbon-12 via protons bombarding it will turn into oxygen. Oh, geez. I just updated you. Okay. Carbon-12 would turn into oxygen 16, and then alpha decay out, and then form back carbon-12 and helium. So that there's actually a nuclear catalyst inside of our sun. But the sun, I went to a talk recently at the Institute for Astronomy here. If you look at the sun as far as like an energy, like if you look at the mass of the sun and how much energy is being released by the sun, it's equivalent to the heat of a compost pile. It's like, you ever been to a compost pile and it gets kind of warm? That if you look at the mass of the sun multiplied by, and like, if you consider the energy density and the energy that's released by the sun over its entire mass, it's about that of a compost heap. So at least that's what the speaker said. So it's not like the sun is putting off a lot of energy, but compared to its mass, it's not putting off that much. That's why it's slotted to live about 10 billion years, because it's not putting off that much energy all the time. But for nuclear fusion, up into iron 56 is exothermic, meaning for nuclear fusion, up into the point in time that we get to iron 56, the binding energy of the nucleon goes down. So the nucleus becomes less massive. After iron 56, when iron 56 is fused, it becomes the reaction becomes endothermic. Energy is absorbed. So this is why we have what's called a type 2b supernova explosion. So like what happens for a type 2 supernova, type 2b, is that the core of the star starts getting iron. And the thing is, when iron is fused, it's endothermic. So you have a gas. So stars are plasma, gas. Depends on if you consider either way, it follows the gas laws. So you have a plasma that has iron in it, and then so iron gets fused, and then that causes the center of the star to cool down. And so what happens when gases cool down? They shrink. And they shrink, which actually adds more pressure, which means more things fuse. And when they fuse with iron, it gets colder, which causes it to shrink faster, which causes the center of the star to collapse. And then the forces coming in the collapse, so the equal opposite rule, Newton's third law, right? Star collapses, causes a force going outwards, and then the star explodes. And then the star, as it's exploding though, it does bunch of nuclear fusion and puts off a lot of energy and creates other elements besides iron. And then, iron up to uranium, and also, like I said before, can also be formed by collisions of neutron stars. So what's a neutron star? After the after the so and this only works for stars with 3 solar masses or greater, so consider the mass of the sun 3 times the mass of the sun. Those stars can supernova in a type 2b nova. Our sun cannot do that unless it combines with another star. Then it could. But then the center of the star, though, that collapsed, it will either form it'll form a neutron star, which is a pulsar, or a black hole. So a pulsar, it's essentially a nucleus. It's a neutron star, meaning it's just a bunch of neutrons. So it's really dense, so gravity keeps it together. And and the electrons and the protons, they join together, and under the pressure, they form neutrons. So it's all neutrons. It's like a single big nucleus of an atom, and they spin really fast. So like the sun, for instance, it spins about does a revolution about every 25 Earth days. So I mean, kind of like the conservation of angular momentum. Like maybe you've seen ice skaters when they go like this, and when you bring in your arms, they go like that's that's the conservation of angular momentum. When you bring it in, you have to spin faster versus far out. So if you have a star that shrinks, it'll start rotating very, very quickly. If the star is massive enough, then it forms a black hole, which we also say is a singularity because we see it as infinite density. But I mean, that's also based off of continuous mathematics. We don't really understand what's going on. Let me put it that way. But a black hole, the gravity of the black hole is so strong that light cannot escape it. That's why it's called a black hole. But around it is actually really hot. So really, really hot. But anyways, back to this chart. So take-home message from that, though, is the elements forming up to iron, fusion is exothermic, puts out heat or energy. Elements heavier than iron, nuclear fission. So fusion means bringing together. So you get a bone fusion. You take 2 bones, like usually in your back, and you fuse them together to form one. Fission means break apart. Nuclear fission for elements heavier than iron is then exothermic. So you can see over here, here's uranium. Uranium is when you break it apart, you get some energy. But if you compare the height here, so if you look at this height here, like say you break apart to form iron, versus this here for deuterium, it's even going to be lower for light hydrogen. But I mean, nuclear fusion puts out much more energy, generally speaking, than nuclear fission. So that's in part why we're trying to invest money in this and trying to figure out how to do nuclear fusion in a controlled fashion. Not just in a nuclear weapon, of course, but I mean like to generate electricity, because there's so much energy available in doing so. But so let's then talk about the nuclear fission. So this is we've gotten this down pretty well. So nuclear fission. So couple things to note, if you can see this. So here's the nuclear fuel that we have. We have uranium-235. So if you dig up uranium from the ground, terrestrial uranium here on Earth is about 0.7% uranium-235, and then 99.3% uranium-238. So the 235 is the nuclear fuel. And the reason for this is, so your uranium is 92 protons, so whatever 235 minus 92 is. So just like, electrons, when they have spin up, spin down. So protons and neutrons, they're fermions too. They're spin up and spin down. There's an unpaired neutron in uranium-235, and so a slow neutron is also called a thermal neutron. When a thermal neutron is added to the nucleus, what happens is that it pairs up and it releases something called the binding energy. So the nuclear binding energy. And then what happens is that this nucleus becomes excited. It's a high energy nucleus, becomes excited, and depending on the elements, depending on the conditions, a couple things can happen. The nucleus can emit a photon, which is a gamma ray for nuclear stuff. It can release an alpha particle, beta particle, and those also have photons emitted. But for uranium-235, it'll split, and it'll form various products, and it'll undergo nuclear fission, and in doing so will release lots of energy. Also releases neutrons. So then these neutrons can go and find other nuclei, and then those split, and then the more neutrons are released, and then we have a nuclear chain reaction, meaning that the nuclear fission is then propagated. It can keep on generating more and more, more and more fission. So then it'll heat up. So energy will be released. Uranium, it's pretty good. It's a pretty good nuclear fuel. It doesn't have so some sources think that the initial, where does the neutron come initially? Things can undergo spontaneous fission. Most sources agree that the uranium-235 will undergo spontaneous fission, and those neutrons will then go, and then that's where the nuclear chain reaction starts. Other elements that can fizz, so plutonium-239, that's another one that we use quite a bit. That one there, plutonium has a really high rate of spontaneous fission. Californium has an even higher rate. They happen really fast. But plutonium-239, this is the preferred material to use in nuclear weapons. So for nuclear weapons, the uranium bombs, the critical mass for uranium is around 50 kilograms. So and they're real simple. They're kind of, as far as nuclear weapons are concerned, they're really simple. All you got to do is take two unequal masses that they combine together to form 50 kilograms. It'll blow up. Plutonium, though, its critical mass is around 5 kilograms. But if you were to take say you take 3 kilograms, 3 kilogram plugs and try and slam them together, what'll happen though is that the rate of spontaneous fission is too high in plutonium, that it'll start to react too early, and then it'll explode, but it won't explode with a very high yield. That's what so a lot of the bombs that North Korea were blowing up, they were saying like, oh, it was a success. I'm like, no, not really. Didn't work. They had one that went up to 100 kilotons was the highest they had. But they said it was a hydrogen bomb. I don't think it was a hydrogen bomb. I think it was something called a boosted fission device, but I can tell you that later. So plutonium bombs, though, they have to angle the bomb. They have to angle the material so it compresses down. It's really hard to do. Actually, it's not a simple thing to do. It's pretty hard to make a plutonium bomb. Uranium bomb, pretty easy. That's what. So North Korea has plutonium bombs. They figured it out mostly how to do it. Iran, they're trying to do uranium bombs, so they're easier to make. So okay, well let me go talk about nuclear power. So what do we use nuclear materials? What do we use it for? We use it for nuclear power. So same idea. This one this is a pressurized water reactor. Okay, there's a couple different types of reactor. The general idea is that you have a nuclear core, and it generates heat, and then that heat is transferred to water some way, shape, or form.
So water is a really good material to put in a nuclear power plant because it slows the neutrons down. So fast neutrons can turn to slow neutrons, which then can be used to split the elements. And these control rods, so these control rods right here, what they do is they absorb neutrons, and they slow down the nuclear reaction. So I remember going to the archives in Washington, D.C., and the first uh, nuclear reactor, at least not the natural one. There are actually some natural nuclear reactors. There's one in Okolo, Africa, they found. But there's been, so there's actually natural nuclear reactors, fission reactors on Earth. At least there were. They've all burnt out now. But the first human-made one was in Fermilab, and I mean it's kind of funny. I mean, look at the pictures and look what we know now. Their control rods were basically beryllium duct taped to 2x4s. So there was a pile. So they had uranium oxide that formed a pile, which means they took a uranium oxide and they formed a pile of it, and then they would remove these 2x4s that had beryllium duct tape to it, and then it would get hot in there. So because it was a nuclear reactor, and the workers there that were doing this, they were like, they didn't have shirts on because it was so hot in there. Like, oh, I'll just go around with my shorts and no shirt because it's hot in here and I don't want to get too hot. And there's also a guy sitting there with an axe. There was a bunch of control rods suspended over the ceiling, kind of like a chandelier, with a rope tied to it, pulleyed down. But this guy's sitting here with an axe, and if they said axe it, he would, whack it with the axe, and the control rods would come down. So that's a term still used. So if you are on a nuclear sub, a nuclear power plant, they say axe it, which means that the control rods just go down, and then turns off the nuclear reactor. But the but is, though, that the stuff that's in the core, it's hot. So hot means a couple things in nuclear science. Hot means it's radioactive, but also in the same, it's literally hot temperature-wise. So like in Fukushima, one of the issues is in the storage facility and in the reactor. So when the tsunami came, the axe worked. The control rods went down and closed and turned off the reactor, but the reactor is still hot. It's still radioactive, and it's hot for a while because the products that are generated from the nuclear reactor are also radioactive, and when they decay down, they release heat. So it takes a while for, it takes a long time for that stuff to decay down. Like tens of years, I should say. So it takes tens of years for it to decay down where it's not hot anymore. Like hot as in it's hot to the touch. And what happened in Fukushima is that the heat in the core built up, and then it caused so much heat that broke the oxygen hydrogen bonds in water, and then it exploded, like chemical explosion, not nuclear explosion. And there was a meltdown too. So the meltdown, they take the uranium and they coat it with another metal like tantalum that has a really high melting point. If it gets too hot, the cladding will melt, and then that's the meltdown. Then some of the products can come out. Okay, so this reactor, this is a pressurized water reactor, which means that the water here is pressurized, and then it transfers heat to other water, which then drives a steam turbine. So there's also boiling water reactors, where here in the nuclear core, steam is formed directly, and then this steam then goes and turns a turbine. So, but the steam here in nuclear power plants, we only use saturated steam. We don't superheat it. So, because we don't like to run that hot. Nuclear power plants are usually run at about 500 Celsius, and a candle flame Just like when you like a tea light candle flame is usually 550 to 600 Celsius. So a candle flame is hotter than a nuclear power plant because we don't like to run our nuclear reactors that hot. And a nuclear core of a nuclear power plant is probably about 4 times the size of this desk area here. So it's pretty small if you think of that, like about a gigawatt. So you can generate a gigawatt of power from something 4 times, like, to the ceiling, maybe not even to the ceiling, like couple, like 3 or 4 feet from the ceiling and twice the width. A box that big can generate a gigawatt of power. So that's how much. So like Maui, for instance, we have about I think we have about 400 megawatts on this island. So I mean, 2.5 times the electricity production of this island could be made, something that big. So a lot of energy in nuclear power. But that's a commercial nuclear power plant, and what we do is we enrich our uranium to about 3%. So meaning uranium 235.
How?
How you can what? You can, yeah.
Is there another technique using like lasers?
Yes, that's what Israel does to make nuclear weapons. But,
I think Brazil does that too.
Oh, really?
I think
Okay.
they developed it actually.
oh yeah, okay.
It's easier with the centrifuges though. It's
Yeah.
just like, unlike the
It's the most common.
Centrifuges, yeah. That's what Iran's doing. That's what
They said
it is.
that they had a plan to enrich it to 20%, but I don't know how people see that.
And also it's like most bomb units take up to like 90% though. So
Yeah,
it's-
or higher, yeah.
I mean like 20% for this reactor is bombs.
20% is considered ultra high enrichment. So the argument that I would have, I mean, so if you have something 4 times the size of this desk is for a commercial nuclear power plant. If you enrich it to 20%, you can make it smaller, maybe like half the size, like the size of this podium. Then would then be your nuclear reactor. But I mean, to enrich the stuff, I mean, either a laser technique what we use here in the States, we make a compound uranium hexafluoride. So it's also known as yellow cake because it's yellow. Okay, so and it has a boiling point of around 50 degrees Celsius. So what? Well, do you remember Grand's law of fusion? Do you remember that? That the lighter gases diffuse faster. If you heat something up and you centrifuge it, like you say, then the lighter elements will spread out faster. So the lighter uranium will, and you have to do it quite a bit to purify it. It takes a lot of energy to do this.
That's
what?
The downside.
What's that?
That was the downside to it compared to laser.
Oh, it uses less energy?
Lasers, yeah, really.
Okay. Yeah.
And it's more eco-friendly.
Well, you need less material. It's smaller. Yeah. So, but either way, I mean, even using lasers or uranium hexafluoride, it still takes lots of energy to enrich uranium. And if all you're going to do is make your reactor smaller, that's not that big. I mean, either Iran hates money or they're making nuclear weapons. I mean, because the cost of it's not like you're making that much of a difference. I mean, like a submarine though, like a nuclear submarine, their reactor size is on the order of liters, like 1 or 2 liters, and they used chemical or weapons grade uranium though for that, so very enriched. But the other thing is if you concentrate down the nuclear fuel, then now your reactor is also more unstable. So you have a more expensive reactor that's more unstable, that is harder to control. It's more likely to melt down. So it's really kind of a bad idea. You can also do what Canada does. Canada, they use heavy water reactors. They use D2O, 2 deuterium oxygen.
and they don't even need to enrich. That's a better neutron moderator. They don't even enrich their fuel. They just put in uranium from the ground, and then the nuclear reactor runs off of that stuff. So if you want to go really, really, if you want to be eco-friendly, then yeah, do like Canada does. But okay, so we're trying to figure out how to do fusion. We don't know how to do it yet, but let's see here. I think you guys want to know how nuclear bombs are made? Now that I'm being recorded. So I mean, the simple one, the little man, and the one that was dropped on Hiroshima, basically just had it wasn't explosive, but explosive pushed a cylinder into like an open cylinder, and this was around 50 kilograms, and then that caused an explosion. It was equivalent to about 20 kilotons of TNT. So the other way you can do it is you can take something made of plutonium and you can compress it down, and you only need about 5 kilograms for this, and similarly you can get a 20 to 100 kiloton explosion from plutonium. And what you can further, I think this is what North Korea did. You can further boost it if you put tritium. If you mix tritium in with this mix, you can create what's called a boosted fission device, which then can have a 100 kiloton to about 500 kiloton explosion. So if you add tritium to one of those bombs, and what's it?
Less than 2% of it actually triggered.
What do you mean less than 2?
Less than 2% of the bomb actually detonates.
For which one?
For Hiroshima.
Oh yeah, I don't know the exact number.
I
But
think it was less
yeah, but that's still. I mean, with nuclear stuff, the E equals mc squared, a little bit of mass is a lot of E. Yeah. Has anyone ever been to Hiroshima? I've been to here. I went to here. Yeah, I did. You guys go to the museum? That was pretty.
than 2%. No, I'm scared for life.
I went to Hiroshima. You saw it. You went to the Peace Dome.
Oh yeah. Were the buildings still there?
Yeah, the building's still there, but it's just like all rusted.
Yeah. Yeah, that's kind of freaky deaky, you know. To see that stuff. Ugh. I've never been to Nagasaki. Closest thing I saw was, remember there was a Wolverine was there in one of the movies, the X-Men movies.
Oh.
So then you can also have so the more advanced nuclear weapons, you have a fission bomb connected to usually something has a plutonium core, and around it you have you can have tritium and also lithium deuteride, and those combinations you can form beryllium and helium via fusion, and these put together, this is known as if it's tritium and deuterium, it's known as a hydrogen bomb. Usually the lithium deuteride, though, we still call this is called an H bomb. And they're also called thermonuclear bombs. And the reason is, so the fission bomb goes off first, which provides the activation energy to set off the fusion bomb. So that's what they call thermonuclear bomb. And the way I've drawn this one is known as a neutron bomb. So a neutron bomb, this weapon would release a bunch of fast neutrons. So the slow neutrons are the ones that initiate the nuclear fission for for uranium, plutonium, californium, that kind of stuff, thorium. The fast neutrons, they cause really bad harm to biological things. So the idea is, well, what if you wanted to drop you went and you dropped a neutron bomb over Pearl Harbor, you kill everyone there. Later on, you can take and then grab all the equipment. So that way, like, oh, now we got warships and other things and tanks and stuff that we got from that target. What you can do is you can coat the outside of the bomb with depleted uranium, so uranium-238. And if you do that, you can get an even higher yield from the bomb, because then the fast neutrons will fizz the uranium-238, and then you get more energy from that. So, and then it's no longer a neutron bomb. So, like, the biggest bomb ever detonated was the Tsar bomb by Russia, and that was 50 megatons. Allegedly, they have up to a 100 megaton bomb, but they didn't. The highest they ever tested was the 50 megaton. The biggest ones we have in the United States is about 25 megatons. Those are the Minutemen, but we don't have too many of the hydrogen bombs. They're not that useful because they're huge and big and they could blow things up. We tend to have smaller weapons, and we have lots of them. We used to have 30,000 nuclear devices. We have about 2,000 deployed now, I think. So that's plenty, of course. So there are many fewer nuclear weapons now than there were. Like at the height of the Cold War, there was quite a few. But I don't know. Anybody have any questions so far? Okay. All right. So where are we at? I wanted to do a couple equations for you. Did I put it on here? No, I didn't. Okay. I wanted to just. So what do we care? Who? What? Why? Know that you get your radiation from natural sources. That's basically where you get your radiation from natural sources, unless you smoke. Now I must have done the problem session. Sorry, not March. This one? No, it's not. Here we go. So you will have to know how to do nuclear equations, and the way you do these is make sure the top numbers and the bottom numbers are equivalent. So, meaning for this one, this thing here, whatever element here, the bottom number is 85 plus 2, it's 87, and then the top number is 217 plus 4, this is then 221. So whatever element number 87 is, I don't know what the heck it is off the top of my head. Element number 87 is francium. Poor France. The element that's named after them only exists for a really, really short period of time. But all I did, though, I just knew it had 87 protons because of these bottom numbers. That the 85 plus 2 has to be 87, and then the 217 plus 4 has to be 221. I just looked up element number 87, it's francium. Does anybody have any questions on how to do that one? Huh. So what about the next one? Plutonium turns into americium plus what? What's the top number? 0. What's the bottom number? -1. That's beta decay. Does this make sense?
Does anybody have any questions with this so far? It's going to be positron emission. Oh, wait a second. It's going to be. I'm sorry. Jeez, what am I doing? Yeah, it's a positron. Because the top number is 0, the bottom number is +1. That's positron emission. So what about the next one? What's D?
What was that thing? Beta?
Well, it's electron capture.
Electron?
Yeah, sometimes called K capture. It's this bottom one. Proton absorbs an electron and becomes a neutron. Here's positron emission. Can you see that, or? Yeah. And then just photon. This is the photon emission on these. This is just like an excited state. Has anyone ever gotten a bone scan before? I have. Am I the only? Okay, you got a couple. You're given technetium-99, and it's the way it's formed. You form it from molybdenum, and it decays down into technetium, and it has an excitable nucleus, and it has a half-life of 6 hours. The giving off gamma rays. So that's what a bone scan is. Technetium itself beta decays down, but what they use in the scan is the bone scan is the excited nucleus. Okay. Oops, wrong one. So other questions so far? All right. So I wanted to do this. This is not on the test, but I thought I wanted to do this problem anyways. So calculate the quantity of energy produced per gram. I'm going to do mole. Mole, the reactant for the fusion of, I guess I could do it per gram, but you do it per mole anyways. For the fusion of tritium with protium to form helium. So we have to find the mass defect. So, which means, so you have to look at H3 plus H1. This is going to be, so 1.007825 and 3.01649, and add those together for 83204. Okay, so that's the mass, atomic mass units there, and then compare that to, then we're going to subtract out 4.0022603. So this 4.023, that's the mass of hydrogen 1 and hydrogen 3, so protium and tritium together, and then helium 4. Subtract that 1, 7, 2, 1, 2. Atomic mass units. And then, shoot, what's the? It's the mass of carbon 12. And So then the conversion here, so 0.021271 AMU times the energy is 931.5 mega electron volts per AMU. I'm gonna use my calculator for this. Zero two one 27. So this is 19.81 MeV. An electron volt, so just so you know, an electron volt, this is 1.6 times 10 to the minus 19 joules. So 19.81 times, so mega is 10 to the 6. 10 to the 6 times 1.6 times 10 to the minus 19 joules. So times a million, 6 times 1.6 e minus 19. And we get 3.17 times 10 to the minus 12 joules. So you're like, wow, that's nothing. But that's for 1. So for 1 mole, you multiply by 6.02 times 10 to the 23rd. And so then this becomes 1.91 times 10 to the 12 joules, or 2 trillion so 1 mole of that gives you 2 trillion joules of energy. That's a lot of energy. So that's how much energy is. The whole point of this is saying, like, there's a lot of energy in nuclear reactions. In this case, nuclear fusion, right? So a lot of energy, much greater than anything we see in chemical things. So, all right, well, we can do more if you want more part. That's okay. How are we doing this? Right? Anybody have any questions? So we got one more class. Oh, a couple things. Does anybody want to take the final and testing center? I've asked this a few times. We have one. Anyone else? You don't have to tell me. Okay, I'll tell you what. You don't have to admit it. I'm sorry. If you want to, sorry, I'm breaking purple laws as we talk. If you want to take the test in the testing center, email me and I'll make sure your name gets in there.
I do.
Okay. Do you want to take it before or after, or same time?
Same time.
Okay. Yeah, and if anyone needs to take his or her class test beforehand, let me know. It's kind of weird here at Maui College because our graduation's on Thursday, so we're starting finals on rather than getting study days. So if you want, if anyone wants to, please email me. So we have 1 day left. And I was going to do a review, and I think the easiest thing for me to do is go over the previous midterms. Which one do you want me to go over, the first midterm or the second midterm? First? Okay. All right, so we'll go over the first midterm, then next class kind of thing. So, anybody have any questions on anything? Not like, all right, so I'm inclined to end class 10 minutes early, especially now that I'm on another watch list from the government for talking about nuclear weapons.
At least I have the good sense to put it on the internet, you know. So, all right. So, see you later. Or I'll go ahead and turn this off.
Oh,